Right now, you are living through the birth and rapid evolution of a new kind of intelligence, AI.
Rival tech luminaries who have already reshaped our world are in an arms race. Recent polls suggest 70 to 90% of all CEOs plan to invest heavily in AI behind them.
The numbers are staggering, amounting to hundreds of billions of dollars in the next few years. Governments and regulators are stepping in as well, setting the stage for a global paradigm shift.
But have you stopped to understand what AI really is? Are you prepared for a world where AI will impact your job, your health, your relationships, and maybe even the nature of your humanity?
I'm Charlie Stack.
I am Lax Srinivasan. We believe your success, our success, depends on us starting to have a different set of conversations about AI.
Join us as we get to know our new neighbor. Welcome to the machine. Today, we're going to talk about scientific discovery and innovation. Machine intelligence is shaping up to be one of the most important innovations of our lifetime, but we're still just figuring out what we're going to use it for. One possibility is that AI becomes a sort of super accelerant for scientific inquiry and innovation, unlocking seemingly impossible problems and also revealing complex ethical and societal issues in the process. Joining us today is AI researcher Mark Woodward. Mark has a comp sci master's from Stanford, a PhD from Harvard, a decade of applied AI research and field experience, a residency with Google Brain. Suffice to say, I think Mark qualifies as an AI expert who has worked on the bleeding edge of the field. We invited Mark to chat with us today because in his next chapter, he's turned his attention to the field of cryonics. If you're like me, cryofreezing and preservation feels a little like a sci-fi fantasy made in Hollywood. Picture astronauts being frozen for deep space travel maybe 1,000 years from now. But the reality is that a technology like cryogenic life preservation may be closer than we think. And that's because we already understand roughly what is needed to make it work, and because machine intelligence is so well positioned to help guide us through many of the most complex remaining scientific challenges. Mark, welcome to the machine.
Thank you for having
me. For starters, tell us about cryonics and why you've become so interested in the field.
Yeah, so obviously my expertise is in machine learning and AI, and I've sort of always been interested in that. Young child, it was playing with electronics. I would always anthropomorphize certainly my little stuffed animals, and then all my remote control vehicles, they had personalities of their own. So I always wanted that AI. I didn't know any engineers. I thought there wasn't a future in it. So I made a conscious decision in high school to not pursue any of those interests. And then that kind of caught up again with me maybe junior year in college. I couldn't resist anymore. My brother had an idea for a startup. We were in the Bay Area. And so over a summer, I taught myself, how to create some dynamic websites, and then I was hooked and just came back and switched my major. So I've been back in AI the whole time. In terms of cryonics, and maybe some definitions are good first. So cryogenics is just the study of materials at low temperature. Cryobiology is the study of biological material at low temperature, so tissues and blood and whole organisms at low temperature. And that's a very respected field that's been around for a long time. The conferences, these are, it enables, like saves lives, creates lives. So, storing of blood, storing of eggs, embryos, and then also a lot of cell lines for research in drug discovery. But yeah, so that's cryobiology, very mature field, kind of focusing now on organ preservation. They're focused on organ preservation, and also another big push is preserving organisms or species that are going extinct. So that's kind of a problem right now. Coral, there's a lot of species of coral. They're trying to preserve those. And then there's cryonics, which of course is preserving whole humans. And I have not met a single cryobiologist who states that as their goal. They might have that, but they're playing it pretty close to the chest. But for me, I don't think it's such a controversial subject. We have treatments today that people died of, for diseases that people died of 5 years ago. COVID is a good example of that. There's a number of cancers that we just keep making progress on. And the same is true today. People are dying of things that we'll, have solutions for, treatments for 5 years from now. Again, other cancers, hopefully Alzheimer's disease. So preserving somebody or giving them the option to survive to their treatment seems like a good goal to me. But yeah, so I was deep in AI and working on preference elicitation. So figuring out what humans want the system to do and align with those preferences. And I started following the cryobiology research and kind of identified this as a real problem and something that I think should exist in the world. So my research has kind of shifted into that.
And Mark, that sounds fascinating. What a great example of a machine to talk about, Charlie. That could potentially change humans as we know it today. Potentially, but what is kind of one thing? I mean, where is that from AI to the cryo? Is some personal experience?
I wish that I had that. I mean, yes, I have a parent that passed, and obviously I would like to preserve them. She was a wonderful person, but no, I think we all have that fear of death. When we realize at a young age that, wait, we're just going to cease to exist, and for the religious among us, that there is a life after that, so that can be comforting. And then also for other religions have wonderful, like, you pass on the good you do in your life is passed on. I think that's great as well. But for being an engineer, we are just, in my mind, a machine, and there's no reason that we shouldn't be able to preserve that machine, keep it running well if we can repair it. And there's a lot of research going on in that direction, repairing, so regrowing the thymus, reseeding stem cells, clearing out plaques from arteries. You probably see this is just general medical advancements. But if we wanted to say, like, 10, 20 years from now, like, nobody who wants to survive dies, then we need kind of a backstop, some sort of safety net. And I think cryonics is that safety net.
Yeah, that's the coolest use case I've ever heard for AI.
But Lex, right, it begs the question, Mark, you're admittedly, not a cryobiologist or but by trade. Is it just pure hubris that leads you to believe that you can help the field with AI? I mean, you're, as an AI researcher, how does AI get involved in solving a problem like this?
Total hubris. Totally agree. Yeah, I think that, I don't know, I speculate, and maybe physics is the same way, but the computer science has there's such a broad space of things that can be created that it kind of builds this confidence in yourself that I can do anything. Yeah. So maybe I had that. I definitely should have been much more humble. The subject matter is much more difficult than I thought. The general chemistry is fine. When we get into organic and biochemistry, it is much more complex than I ever imagined, and I have so much more respect for doctors and scientists than I ever did. But yeah, so how does machine learning actually tie into this? Yeah, so the problem we obviously preserve things like I mentioned, cells, tissues, blood, but the problem is just with scale. Well, first let me say, okay, so what's the problem as you preserve it? What goes wrong with the tissue? Well, as you're cooling it down, if you cool slowly, the problem is ice formation. So ice starts to form, and the ice that's formed is pure water, and it pushes out the other things that are in the tissue, and concentrations get messed up. So, and that messes with cell walls, can denature the proteins so they fall apart and or unfold, and it can mess them up to a point that they can't then recover if you warm them up and resume normal function.
I don't want to be frozen slowly, because then ice crystals form and it destroys my cell tissue in the process. So it's sort of purposeless.
That's right. Right. So you want to freeze quickly. And if you freeze quick enough, you actually, what's happening as the ice crystals forming is the little molecules are falling into place in the nice crystal lattice of the ice that's being formed. But that takes time. So if you pull out the energy, and that the energy is just the wiggling, or the heat is just the wiggling of the molecules. So if you're pulling that out fast enough, they slow down before they have a chance to fall into that nice lattice. So they kind of slow down, stop in place. And that's called a vitrified state, or a glassy amorphous solid state. Those are all terms of that. But yeah, so that's the goal that we'd like to get to. So you want to cool the person fast enough. But if you cool really fast, and the way we cool again is we apply something that's really cold on the outside of the tissue. And the problem is the inside of the tissue is warm, so you have to allow that heat has to transfer out to the edge and then be cooled at the edge. So there's that that thermal gradient,
an air conditioner,
as we call it. Yeah, it takes a while for that heat to propagate, and the thicker the tissue, the longer it takes to propagate. You could apply something really cold at the edge, and the problem there is the difference in temperature from the outside to the inside is so great that it creates thermal stresses and can actually crack and damage the tissues. So this is like dropping an ice cube in coffee or something. It'll you hear the crack, 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 and that's because of the large thermal difference between the inside of the ice cube and the outside of the ice cube. That's kind of the opposite case.
That doesn't sound like what I want to have happen when I get cryo.
Don't want to have that happen. So we have this tension, like we want to cool it quickly, but we can't cool it too quickly as the thickness of the tissue grows large. So that's why we can preserve things that are really thin, but we just haven't gotten to the scale of even mice yet. So that large of tissue. What people are working on and how machine learning will come into this is we have cryoprotectants. So these are solutions, molecules that we inject into that we perfuse the tissue with. So it goes throughout the tissue and it changes the characteristics of that. So it either makes, the ice doesn't or the nucleation points don't form as quickly, or it lowers the freezing point, or it slows the growth of the ice crystals. But it changes the properties such that we can avoid those thermal cracking, but still cool faster than the ice can form.
So Mark, is the kind of the central kind of let's call it blocker to why it's not been possible, that AI is making it possible today? Is it in just trying kind of lots of different permutation combinations of these this agent, or the thing that's going to try, and you're able to simulate? Like what is the nub of where AI is making it possible? That wasn't possible before.
Well, I would say that AI is not being used for this, or it has in rare places, but that is what my intention is, and that's where my research is taking this to apply. And it's exactly as you say, that right. And the problem with the cryoprotectants, so okay, that's great. We have these cryoprotectants, and we can preserve fairly thick tissue, but the problem is the cryoprotectants themselves do damage to the tissue. So we need less toxic cryoprotectants and better performing cryoprotectants. So as you say, it's in this exploration problem where we need to find that right molecular formula that, or a combination of different molecules that will allow this preservation. And that's where AI can help explore, because it would just be too long to go and do all those experiments. So the proposed approach, and when we talk about other areas as well, this will come in. But the approach is we have a number of these cryoprotectants where we have the molecular structure, and we have the properties of that. So what's its viscosity, what's its thermal conductivity at different temperatures. And so we have that data set. We can train a model on that will predict those properties and this is using machine learning, predict those properties from the structure of the molecule. And then we can go and search the space. So look at different possible molecules and say, this is what we think the properties would be. And this is an iterative process. So then you would take that molecule, the ones that we think will perform well, go out, do experiments with that, and then if it works, then great, we're done. If not, that data gets fed back in, and the model is improved, makes new suggestions.
I'm assuming it's in a simulation. I mean, you're not getting actual volunteers that go through this process, human volunteers.
No. This is like, to understand, it's just really small volumes of the cryoprotectant.
Okay.
You're applying it to cells. Yes. One model organism that researchers have been talking about lately is going with like a zebrafish. So very tiny for a whole organism to be dealing with. Yeah. This is just improving cryoprotectants is a goal of the cryobiology field in general. So this will help with all those other applications in cryobiology, improving the cryoprotectant. It will just so happen to improve with my application of cryobiology to cryonics. But yeah.
And Charlie and I are spending quite a bit of time these days in pharma industry, and this sounds like early stage drug discovery.
That's
And
right.
can you talk? I mean, I've seen examples from that space where they're able to try millions of molecules and things that would have taken years, they're able to do in months. So can you give us some examples of like, what are we talking about here? I mean, what is it? What is the kind of the quantum kind of the benefit that AI is making it happen in this space?
Yeah, I think the big picture there is to be able to explore drugs in well, and also, yeah, drugs and also treatments, but explore it in simulation. And it's generally this iterative process where, you know, a treatment that's suggested or a drug that's suggested that might have the properties you desire is then, you know, tested, and then you iterate on that. And again, it's tested in the lab on small tissue, not on a real human, but it iterates through the whole approval process. But yeah, you're building a machine learning model that hopefully is representative of an organism you care about, or like, you know, a protein. So yeah, so I don't know, maybe you know the structure of the protein you want, like the actual shape of it, but you don't know the amino acid sequence that'll fold up into that shape. And so you need a model, you need a way to explore the space of amino acid sequences to find one that will fold up into the shape that you want. So machine learning helps there. It'll, you know, there's a machine learning model that will go from the amino acid sequence to a shape. And so you can iterate on different sequences in simulation to find one that will produce the shape of the protein that you want.
And so this is, I mean, roughly, you know, it might allow you to explore, you know, millions of different amino acid sequences and narrow that field down to, you know, a few probable, you know, kind of likely, you know, candidates, you know, in a matter of minutes versus, you know, what might have taken in a lab, you know, years and years and years. I mean, is it that sort of quantum leap?
Yep. Yeah. And I mean, the number of possibilities is like explodes exponentially, because you can, you know, for this one, you can have 10 of these, and then for each one of those, there's 10 of those. So that's like an exponential growth of the possible experiments you might want to run. So you really need something that's helping explore that or suggest that space. Or the hope is that if we have something that helps explore that space, we can get to results faster.
Yeah, Mark, as an AI researcher, I mean, is this any different from digital twin that could simulate a business process or I mean, this looks to me that it just happens to be biology.
That's right. That's
all
right.
You're talking about is modeling an organism. Could be a business, could be a process, could be a tissue, and then using AI to really rapidly simulate. You're really compressing time in terms of what it would have otherwise take.
That's right. And so there's a company that I'm the CTO of, January AI, and we do blood glucose prediction. So somebody wears a blood glucose monitor for a week or so, and they log their food, and from that data, we call it a digital twin that we learn from them, and then we can predict forward. If you ate this is what your blood glucose response would be, and that way they can exactly just explore that space just on their phone and not need to actually you know, eat those foods and go through all that experimentation themselves.
Yeah, it's actually interesting you bring that up, Mark, because, you know, you know, sort of the topic today is about the acceleration of, you know, scientific discovery, but, you know, that's an example that's more about the acceleration of sort of personal discovery.
Yeah.
You know, in that case, somebody trying to understand how what they eat impacts how they feel. You know, which can be kind of a hard thing to get your hands around, actually, as it turns out. How do you think about, I mean, as somebody who's been looking at lots of these sorts of problems, you know, maybe for our listeners, how do you think about the application of this kind of AI? I mean, like the image that always comes to mind for me is this is sort of the example of like the flashlight in the dark. You know, it's not necessarily like solving the problem for you, but it's eliminating so much of the bad noise that you don't need to pay attention to from the equation. You know, so otherwise you might search all around a room sort of blindly. You know, instead it kind of focuses you on the the best thing to do, the best options, the most likely options.
Yeah, yeah.
Is there a way to think about how to apply this sort of capability more broadly?
I mean, it is very broadly applicable. I was trying to think before this call about areas where it wouldn't be applicable. For the machine learning systems that we currently have, you need data, and ideally that data comes in IID, so identical and independent distributed. So you're seeing a lot of the same problems. Things like the stock market and prediction, the problem there is it's never the same point in time. Like it's never the same exact circumstances, and it's just one path through. You're not being able to witness a bunch of different stock market trajectories. So because there's only really this one path in time. So areas like that might, although AI is heavily applied in finance, but
it's applied differently there.
Yeah. So Mark, I think that one thing that, I mean, what this has potential, kind of relevance to any AI project. This looks like when you're experimenting with molecules and seeing what it's working, you don't have data, right? I mean, this is almost like a consumer products good company launching a new product in the market. I mean, there isn't. So can you talk a little bit quickly about, how do you tackle that problem when you don't have historical data? Because I mean, it's almost like, it comes to me like this whole thing you have described is a data generation exercise where you model an organism, you try a lot of different inputs, and you simulate and create the output. And perhaps some human could look at it and say, well, did that thing survive or not? And if it's good, so you do just like how Gen AI was trained, right? Through reinforcement learning. So the question is, what is the data set that you have to begin with?
It's an excellent point. Yeah, there's that cold start, and you're right. At that ground zero level, there isn't an application of machine learning. You can't directly apply to it unless, once we start to get into the larger models, the large language models or vision models, where maybe you could transfer something from another task onto this task. The protein folding one is pretty broad there. So you might be able to pull some tools that have been trained on another data set that would be relevant to yours. But yeah, in the beginning, I mean, the first experiments you're doing, you are collecting the data set that would later be useful for a machine learning system.
So my point is that I know that a lot of times, we hear that, well, I don't have data, therefore I can't really use AI. I think the point is that, if you figure out there's a problem, there are lots of different ways that you can actually bootstrap. Yes. And there are ways now that you can actually create a data set, as you said, from a cold start. I mean, to me, this could be a very interesting area, what you're doing. There could be some parallels others could learn how to bootstrap.
Yes, and there is the traditional like supervised data, the way it comes in, where here's the input and here's what I want your output to be. But then what we've been calling lately is more semi-supervised. And this is the idea that no one actually goes out and labels something, but you have underlying data that's very easy to collect for some reason. So with large language models, so like ChatGPT, you have text on the internet, and so what you can do in a semi-supervised way is you can knock out one of those words and just say, I'm going to pretend I don't know that word, and just from the context, the neighboring words, I'm just going to try to predict that word. So there may be these sort of semi-supervised or unsupervised techniques that are applicable when you don't have labeled data yet, but you might be able to still collect data, still have some measurements. Yeah. And then of course there's other hybrid approaches. So where a scientist there's a full like mechanistic approach, and this is used in medicine a lot, where a scientist just writes down the formulas for the evolution of a biological system. And then you just use that as your simulator in the beginning, and it suggests, bad things that are going to happen. And so you can use it to explore. And there's no learning in that at all. On the full other extreme is like end-to-end learning, where you have a machine learning. It's just learning everything from the machine learning model, and it's learning everything from the data. And then there's in between where the scientist still specifies some of the formulas, but there are parameters in that are still learned from the data, from the limited data you have. So usually the accuracy goes, the more you give up control and let it learn from the data, the higher the accuracy, but the more data you need. So you might start on that end of the scientist and push over to the full end-to-end machine learning.
It's great.
So Mark, before we begin to wrap here, how long is it before I can freeze myself and wake up at a later date?
Yeah, so again, we are freezing tissues right now. So if we hit that right formula, again, that's not the objective of the cryobiology field in general, but if we did hit that, then yeah, it could be tomorrow we could have the technology. We just need that biocompatible, cryoprotectant. That said, there's a possibility that there is no molecular combination or a combination of molecules that would allow, an organism as large as a human to be preserved with the technologies that we have. So this is a good kind of call to arms that if we can't do it that way, then we need to take a different path. And so if you're a physicist out there or a chemist I guess physicist or a chemist would be or a material scientist possibly, please reach out to me. The holy grail really would be what we call volumetric cooling. So instead of cooling from the surface where you have this temperature gradient and the potential of cracking, if we could cool uniformly in the way that we can warm, so a microwave can warm something up uniformly, and that way there aren't these large, in a microwave it's not very precise, so there are these hot spots, but when we warm in cryobiology, we can do it in a way that it is very uniform. So warming, we warm volumetrically, but we'd like to be able to cool volumetrically. And there are some crazy techniques for volumetric cooling. One is called magnetic refrigeration, which we could get into some other time. And another is one that quantum mechanical scientists use. It's called Doppler cooling, where you take advantage of the fact that a molecule is moving towards you and you remove some of the energy there, and then you're removing the energy, and so basically it slows the molecules down, but using something like the Doppler effect. But yes, if you think of something crazy like that, or maybe some endothermic reaction, please reach out to me, or even if you're not thinking about it, you just want to talk about that, we'll put my contact information out there.
Great. Yeah, we will share as we release the episode. Thanks.
Yeah, and thank you, Mark. Great to meet you. And I know this is kind of way out there, but I can see a lot of what you're doing. There are a lot of takeaways that anybody out there could use when it comes to AI. So I appreciate your being with us.
Yeah, my pleasure. Thank you for having me.
As we sign off, maybe, Mark, one final question that we like to ask all our guests. One thing you're really excited about, one thing that really concerns you as you think about AI and where we are at this point.
Yeah, so excited about applications in medicine, so drug discovery and things that I'm working on. Obviously, cryonics, I'm excited about. Worried about my former research that I've kind of put on hold. So this alignment of AI, we're creating more powerful AI systems, potentially more intelligent than humans. We just need to make sure that they are aligned, doing the things that we want, have the goals that we want them to have. Yeah, that's a concern. It feels like we're threading a needle.
I've heard just because he can, maybe you don't want to do it. And this particular machine, Mark, we discussed today, I would say we should definitely think about it, even if you come up with a breakthrough.
Right.
So, excellent.
Thanks so much. Great to have you on.
Yeah, thank you, Mark.
Thanks for having me.
Thanks for listening to Welcome to the Machine.
To join the conversation, visit us on welcometothemachine-ai.com.
Special thanks to Spencer Stewart, the Return on AI Institute, and our fantastic production team, Trey, Jojo, and John, for helping bring WTTM to life.
Don't forget to share, like, and subscribe.
See you next time.